Okay, welcome everyone. So in this next set of videos, we're gonna wrap up our treatment of determinants. So far we've kind of discussed what a determinant is, different ways that we can calculate determinants, and in particular, what is really useful about determinants is that they can indicate whether or not a matrix has an inverse, right? If the determinant of a matrix is not equal to 0, then we know it has an inverse. If the determinant of a matrix equals 0, then we know it's not invertible. And we've also seen that whether or not a matrix is invertible also has some ramifications on solution sets for systems of linear equations and their corresponding matrix representation. So I want to explore in this next set of videos how we can use determinants to help us solve systems of equations. And we'll derive what's called Cramer's rule, which is a nice way of connecting determinants to solution sets for systems of linear equations. So let's imagine we are solving the following system of two linear equations with two variables. 3x1 minus 2x2 is equal to 6, and minus 5x1 plus 4x2 is equal to 8. We certainly have lots of different methods for solving a system of linear equations like this. But let me, before we state Cramer's rule, it's going to require us to be comfortable with what we're calling, I'm going to denote matrix A sub I evaluated at column vector B. So let's back up. Let's say I've got a square matrix A, and so A1, A2 up to AN. These are denoting the n column vectors that make up matrix A. And let's consider some column vector B, right, which is going to have the same dimensions as each of the column vectors in matrix A. So if I replace the ith column of matrix A with this vector B, I'm going to denote the new resulting matrix A with a subscript I. So this is denoting which column of matrix A have we replaced with vector B. So in other words, I would scrape out whatever column vector AI is, and I'm going to replace it with whatever column vector B is. So let's take a look at a concrete example. So let's say we have the matrix of coefficients for this linear system is matrix A. So its top row is 3, minus 2, and its second row is minus 5, 4. And then we've got column vector B is given by the coefficients on the right side of this equation, namely it's a column vector, first entry 6, and the second entry is 8. And then let's consider what these matrices would look like, each of them. So what would matrix A1B look like? What would matrix A2B look like? Well, A1B is the matrix that we're going to replace the first column of matrix A with 6, 8. And I don't do anything to the second column. So the first column is no longer 3 minus 5. We replace it with 6, 8. And the second column remains the same as, we don't change the second column of this matrix. And similarly, A sub 2 evaluated at B means we now replace column 2 with 6, 8. So column 1 is still 3 minus 5, but now column 2 gets replaced with 6, 8.